Property of non-corresponding cofactors. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to recap what we have already covered in our previous lessons. Up until now, we have been focusing on how to expand a determinant. As you remember, the standard method involves taking the elements of a specific row and multiplying them by their corresponding cofactors. To be more precise, when we take the elements from row I and multiply them by the cofactors belonging to that very same row I, the resulting sum gives us the actual value of the determinant, which we denote as delta. But today, we are going to explore something a bit more unusual. I want to show you that an interesting algebraic property emerges when we stop being orderly and instead mix the elements from one row with the cofactors from a completely different row. This specific phenomenon is what we call the property of non-corresponding cofactors. Keep this term in mind, as we will be breaking down exactly how this works in the next few slides. Understanding the concept, the property states that if you take the elements from any one row, or even any one column, of a determinant and multiply them by the cofactors belonging to a different row or column, the sum of all those products will always equal 0. To be more precise, let's look at the mathematical statement. Suppose we have the elements of the ith row, which we can call a sub I1, a I2, all the way up to a In now. Let's take the cofactors from a different row, the jth row, which we'll call a j1, a j2, up to a j, and the rule is simple. As long as I does not equal j, then the sum of a I1 times a j1, plus a I2 times a j2, and so on all the way to a In times a jn, will always result in 0. I know that looks like a lot of notation, so let me give you a conceptual analogy to help it stick. Think of this like a lock and key mechanism. You can think of the elements of a specific row as keys that are uniquely designed to fit the locks, which are the cofactors of that exact same row. When they match, they open the determinant to reveal its value, as we saw in our previous lesson. However, if you try to use the keys from row 1 to open the locks of row 2, they simply won't fit. Instead of producing a value, the numbers interact in such a way that they cancel each other out perfectly, leaving you with nothing but 0. Now that we've introduced the topic, let's dive deeper into what this property actually means. In the next slide, we'll look at the underlying logic of why this cancellation happens so perfectly. The logic behind the property. Now, you might be wondering, why does this happen? Why does the sum always result in 0? To understand the logic behind this property, we need to look back at a fundamental rule of determinants that we've studied before. If any two rows or any two columns of a determinant are identical, the value of that determinant is always 0. Let's connect this to what we just discussed. When we take the elements from row I and multiply them by the cofactors of row j, what we are actually doing is performing a calculation that is equivalent to finding the determinant of a brand new matrix. In this new matrix, we have essentially replaced row j with row I. Think about what that means for the structure of the matrix. Row I is now appearing twice, once in its original position and once where row j used to be. Because this new matrix now contains two identical rows, its determinant must be 0. And since this sum of products is exactly how we calculate that specific determinant, the final sum must also be 0. We will see this logic in action with a concrete numerical example in the next few slides. Step-by-step example. Now that we have understood the theory and the logic behind why this property works, let's move from the abstract to the concrete. To demonstrate this property in action, let us work through a practical, step-by-step example using a 3x3 determinant. Please look at the determinant shown here, which we will call delta. It consists of the first row containing the numbers 1, 2, and 3, the second row containing 4, 5, and 6, and the third row containing 7, 8, and 9. To test the property of non-corresponding cofactors, we aren't going to use the standard method of expanding along the same row. Instead, as we've discussed, we are going to intentionally mix them up. Specifically, we will take the elements from the first row and multiply them by the cofactors belonging to the second row. In the next few slides, we will calculate those specific cofactors and sum them up to see if we indeed arrive at 0. Step-by-step example, continued. First, we need to complete step 1, which is to identify the elements of row 1. Looking at our matrix, the elements in the first row are a sub 1 equals 1, a sub 1 2 equals 2, and a sub 1 3 equals 3. Keep these three numbers in mind, as we will be multiplying them by something else in a moment. Next, we move to step 2. This is where the real work begins. We need to calculate the cofactors for row 2. Now, before you start calculating, I want you to recall the fundamental formula for a cofactor. The cofactor, denoted as a sub ij, is equal to -1 raised to the power of the sum of I and j. Multiplied by the minor, m sub ij, we will be applying this specific formula to each element in the second row in the next few steps to find our locks for the keys we identified in step 1. Now that we have our determinants set up from the previous slide, let's dive into the actual calculation. Step-by-step example, continued. First, let's find the cofactor a 2, 1. To do this, we mentally delete row 2 and column 1 from our original matrix. This leaves us with a 2 by 2 determinant of 2, 3, 8, and 9. Applying our sign rule, -1 raised to the power of 2 plus 1 gives us -1. When we calculate the determinant of that minor, which is 2 times 9 minus 3 times 8, we get 18 minus 24, resulting in -6. Finally, multiplying -1 by -6, we get our first cofactor, which is 6. Next, let's calculate the cofactor a 2, 2. For this one, we delete row 2 and column 2. Our remaining elements form a minor with 1, 3, 7, and 9. Here, the sign is -1 raised to the power of 2 plus 2, which is a positive 1, so the sign remains unchanged. Calculating the determinant, 1 times 9 minus 3 times 7 gives us 9 minus 21, which equals -12. So our second cofactor is -12. Finally, let's find the cofactor a 2, 3. We delete row 2 and column 3, leaving us with the minor containing 1, 2, 7, and 8. The sign is -1 raised to the power of 2 plus 3, which is -1. Calculating the determinant of this minor, 1 times 8 minus 2 times 7, we get 8 minus 14, which is -6. Multiplying -1 by -6, we arrive at 6. Now that we have identified our elements from row 1, let's move on to the heavy lifting. Step 2, where we calculate the actual cofactors for row 2. Remember, to find a cofactor, we use the formula where the sign is determined by -1 raised to the power of the row index plus the column index, multiplied by the determinant of the remaining minor. Now that we have all three cofactors for row 2, we are ready to move to the next slide to see what happens when we multiply our row 1 elements by these specific values. Step-by-step example, continued. Now that we have successfully calculated all the individual cofactors for the second row in the previous step, we move on to step 3, which is the final part of our demonstration, computing the sum of the products. To verify the property, we are going to multiply each element from row 1 by its corresponding cofactor from row 2. In mathematical terms, we are calculating the sum of a 1, 1 times a 2, 1 plus a 1, 2 times a 2, 2 plus a 1, 3 times a 2, 3. Let's substitute the actual numerical values we just found into this equation. We take the first element, which is 1, and multiply it by the cofactor 6. Then, we take the second element, which is 2, and multiply it by the cofactor -12. And finally, we take the third element, which is 3, and multiply it by the cofactor 6. When we perform these multiplications, our expression becomes 6 minus 24 plus 18. If you add 6 and 18, you get 24. So, we are left with 24 minus 24, which equals 0. As you can see, the result is exactly 0, which perfectly confirms the property of non-corresponding cofactors we've been discussing. In the next slide, I will highlight some common pitfalls to avoid when performing these types of calculations. Common mistakes. First, the most frequent mistake I see is confusing corresponding with non-corresponding cofactors. It is easy to slip back into the habit of the standard expansion method we discussed at the very beginning of this lesson. Remember the distinction. If you multiply the elements of row I by the cofactors of that same row I, you get the determinant, represented by the Greek letter delta. However, if you multiply the elements of row I by the cofactors of a different row j, where I does not equal j, the result must be 0. Keep this distinction clear in your mind. Second, watch out for sign errors when calculating your cofactors. When we were working through our example in the previous slides, we had to be very careful with the term -1 raised to the power of I plus j. A common mistake is forgetting to apply this sign to the minor. Always double-check the position of your element to see if the sign of the minor needs to be flipped or kept as is. Finally, be careful with calculation errors in your minors. When you are finding the minor, denoted as m sub I, j, you must delete the correct row and column. This is particularly tricky with the property we learned today. Remember, when you are calculating non-corresponding cofactors, you must delete the row and column associated with the cofactor itself, not the row where your elements are coming from. Staying organized with your deletions is key to getting the right minor. Now, before we wrap up, let's pause and look at some common pitfalls. Even if you understand the concept, it is very easy to make small errors that lead to the wrong answer. Key takeaways. First, let's restate the core rule we've been studying. The sum of the products of elements from any one row, when multiplied by the cofactors of a different row, will always result in 0. It is that simple. To put this into a formal mathematical notation, we can write it as the summation from k equals 1 to n of a sub ik times a sub jk equals 0, provided that I does not equal j. This formula is just a concise way of expressing exactly what we discussed in our step-by-step example. Now, if you are wondering why this happens, and as we saw in our logic slide, it is because this specific operation is mathematically equivalent to calculating the determinant of a new matrix where two rows are identical. And as we know, any determinant with two identical rows must be 0. Finally, keep in mind the broader applicability of this property. This isn't limited to just rows. This property applies equally to columns as well. If you take the elements of column I and multiply them by the cofactors of column j, as long as I and j are not the same, the sum will also be 0. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing our key takeaways. I hope this property makes sense to you now. Great job following along through all these steps.